Okay, so for my project, I wanted to build a predictive model to determine if someone had Down syndrome based on the expression of 77 different genes. I got the data set from the UCI machine learning repository. Going over to the PowerPoint to look at some information on it. Um, so information on the data set. In total, there is 1,080 samples. 570 of them are the control, 510 are the treatment group. Again, they looked at the expression levels of 77 different genes. In total, there are 8 different groups. If there's a C at the beginning, it is a type of control group. If there's a T, it is a treatment group. So the idea for my project, the overall big picture, again, was to determine if someone had Down syndrome based on that gene expression data. Supported projects throughout it also include are all 71 genes required to predict that? How many genes are affected by trisomy? Are there any high correlations between specific genes? And can the models actually predict one of the 8 specific treatment groups or just treatment versus control accurately? So going ahead and diving in to how I explored the data. For one, I just looked over to see what was I working with, and primarily it is numeric data, but some of them were factors. I looked to see are there missing values. I built this little table to do that, to count the amount of NAs per column. Then I determined how many outliers there were, or if there were outliers. I had to do this for each gene and treatment group because you would expect there to be some change because of experimental conditions. So I did this for mean and standard deviation. So with the data, after learning that there were NAs and outliers, I handled the issues using mean imputation. Mean imputation was done at this stage. And as you can see, if you look down here at this table, I redid the table again, checking the amount of NAs per column, and they're all zeros at this point, where before they had values. Then below, I replace outliers using mean imputation. And I printed the amount of outliers per column that had to be replaced using mean imputation, just to make sure we didn't go above the 10%. Then I look at the correlations between the genes, and I actually also tack on the p-value associated to that correlation, just because statistical significance is very important in science. Exploratory data plots that I look over include heat maps. I did a big picture just so you could visualize the correlations. Additionally, I built some pairs panels to look at the distribution and the normality of the data. As you can see here, BRAF 4in down here in this section, it didn't have a good distribution. So I did some log transformations as well. And as you can see, it actually just shifts it completely to the other side of the graph, so it didn't help it out too much. It's still skewed. It did work well, though, with ITSN1, but there were a couple other instances where log transforming it wasn't the best thing for it. So I didn't apply log transformations across the entire data set because it wasn't advantageous to do so. Instead, I chose models that wouldn't be negatively affected if the data wasn't perfectly normal, didn't have perfect normal distribution. Also with picking features to go in, I did a PCA, a principal component analysis. Going down here, I looked at the cumulative variance percent. So I went through and I realized that after 18 of these features, 90% of the variation in the data set was accounted for. So I decided which features to use based on how much it contributed to the overall variation of the data set. I tested all my models using just 18 features and I got lower accuracy values. So I ended up going with 30, which would be 95% of the variation in the data set, and I got much better results doing that. To prepare the data, I divided to training, testing, and validation. I had to prepare a validation data set because I used a stacked learner at the end, and it's already been introduced to the training and testing data. Additionally, I remove 5 samples from the overall data set starting out. I take off all categorical information, and all they're left with is their numeric data. I use this so that I can deploy the model on 5 samples at the end. So the types of models that I built is going to be a little bit faster to go over here. Starting out, I build a regression tree. The reason why I do this is because I wanted to do a decision tree, and regression trees can handle numeric data. I didn't want to bin 30 different features. I knew it would decrease the accuracy. Regression trees can also handle skewedness pretty well, and they're easy to use. Modifications that I made to this tree were a random forest and pruning. The next one that I went down is my neural net. I wanted to cluster the data. I also wanted to do an unsupervised learner so that it could go in with very few assumptions on the data and see if it could recognize patterns. They also handle numeric data well. Modifications that were done to that one are the hidden nodes. Validating them, I did a confusion matrix. My KNN models, I did this because I'm trying to predict a treatment group, and KNN models are a classifying model. It can handle continuous data, and it does cluster well. Modifications, I looked at k-values 2 through 10. I also tested 3 different types of KNN models to pick the best one. To validate the KNN model, I did a confusion matrix. I looked at a multivariate ROT curve and the AUC value. So going back, this is my regression tree, just it running. And then we can look at the values. Okay, so it actually got a 71% accuracy, and this is after the tree has been pruned, so it does have a modification, but it still has a lower accuracy value, so I ended up going ahead and building a random forest. So as you can see here, I also look at with the random forest, it also comes with an OOB estimate error rate, which is just its prediction error rate, which it sat around 7.6%, which is pretty decent. Overall, it also had a accuracy value of 96%, so it was substantially higher than the regression tree. Here is my neural net. Excuse me. So starting out, the neural net did very, very poorly. It had a 33% accuracy rate. So I went in, I modified it, and I altered the hidden nodes, and I actually got it up to up to 90%. So it is a substantial change. With these confusion matrices, going through, I also looked at the sensitivity and specificity values for everything, for each class overall, and as well as the balanced accuracy for each class. So this is where I actually decided which KNN model to use, as well as which K value. So I built a for loop, and it runs all 3 of the types of KNNs, and then it runs it through K values 2 through 10. It then calculates their accuracies, and then I have it down here printing those accuracy values on a graph. And I do that just so I can easily visualize what was the most accurate model to use. And I wanted to use a regular KNN, so I needed to pick which value. And then I also had to decide between weighted and or Gaussian and ranked. And I ended up going with weighted just because it does perform better. So this is where I actually built the KNN models, and no modifications were done at this point just because I had chosen the K value above. So here you'll see that a regular KNN model with a K value of 2 got an 88%. Under the multi-class area under the curve sat at 91%. This is actually just the multivariate ROT curve. This is my weighted KNN. It had a K value of 3. Printing out its results for the confusion matrix, it got a 94%. Additionally, so its multi-area class area under the curve value is 94%, and that is its multi-ROT curve. Down here is where I actually compare all the models together, and I decided which ones to keep and which ones to put into the ensemble. I also decided an ensemble is probably the best way to go just because the neural net model was struggling with an 81% accuracy. So building my ensemble, I did down here. I ended up putting in 2 KNN models, the Gaussian and regular, the neural net, the modified version of it. and the random forest, just because the regression tree did so poorly. Um, the ensemble works by taking a majority vote. It has a 96% accuracy. And as you can see, on some occasions, under sensitivity and specificity, it does well, meaning it gets all of those values 100% correct all the time. But I really wanted to build on ensemble, and we can go back to the PowerPoint, to increase the accuracy. And right now the ensemble has the same accuracy as my random forest. And there's no point of building an ensemble if it's just going to get the same accuracy as another algorithm that's much simpler. Also, I did decide to go ahead and build a stacked learner to try to increase the accuracy as well. And so building an ensemble lets me add a feature. I actually take the majority vote and use it as a new feature. And then the ensemble should increase the accuracy just by reducing the noise. So again, to validate it, I look at the confusion matrix and look at things like accuracy, sensitivity, and specificity. So down here is where I build my stacked learner. And at this point, I'm no longer using the testing and training data. I've switched over to the validation data to test it on. I test with the validation data. So the stacked learner only did slightly better than the ensemble and the random forest. It does significantly better with sensitivity and specificity values per class, but it's only 1% more accurate than the other two models, which I do compare in down here. And because they're all, well, because the stacked learner and the random forest are so similar, even with their sensitivity and specificity values, I actually include it in the deployment as well. So here's where I actually deploy the model. And you see that when I run it, they actually predict, for those 5 samples, they predict the same treatment group. So they work very similar. They have very similar accuracy values, which is what I document under my going forward. One, I do notice I can answer all those supporting questions. Only 30 out of the 77 genes were required. There are high correlations between some of the groups, which means those trends might be due to those genes being in the same pathway. Yes, I can accurately predict not only is it treatment or control, but the exact group. That information can be used later on to see, do certain genes respond certain ways under certain groups versus other groups. You can start to compare things like that. Additionally, from a business perspective, it's not advantageous to build a stacked learner or an ensemble. They take a lot of time because you have to validate every algorithm going in. You have to get the best possible version. You have to essentially massage the data to even run through it accurately and print out accurate results. You have to do that for an ensemble and a stacked learner. And if they're putting out accuracy values and sensitivity and specificity values, just like a random forest, it's just easier and a better use of time to build a random forest. Additionally, my values change very slightly every time I run the model, just because I wasn't able to do a k-fold validation. So there are slight adjustments just because it's making new predictions each time. And that is a downside. I would have liked to have used a k-fold cross-validation, but it's difficult to do in R Markdown and across this many lines of code, where if you're doing something like a random forest, you can easily implement one of those. So I definitely think this is still a good model. I think they're both still good models, but I do think the random forest would be the better option going forward.